Hello and welcome to the CSES Problem Solving Club meetup today. We will be going through the book today. We have a book reading session. If my audio is working fine, please post a message on chat so that I know my audio setup is working fine. Thank you for the confirmation on the chat. All right, so let us begin. We will try to finish chapter 1 today. And the last time we stopped somewhere here, we were discussing the modulo operator, and we learned this little trick that if our modulo operation result is negative, we can just do a plus equals m to make it positive. And often while solving problems, we will need the modulo result to be positive. So that's where we stopped, and now we'll continue from there. So today we have floating point numbers. It'll just teach us a tiny little trick about comparing floating point numbers in a reliable fashion. Let's go through it. The usual floating point types in competitive programming are the 64-bit double, and as an extension in the G++ compiler, the 80-bit long double. In most cases, double is enough, but long double is more accurate. The required precision of the answer is usually given in the problem statement. An easy way to output the answer is to use the printf function and give the number of decimal places. An example given here. For example, the following code prints the value of x with 9 decimal places. So this is an example of the format specification. A difficulty when using floating point numbers is that some numbers cannot be represented accurately as floating point numbers, and there will be rounding errors, and that is why we cannot do a comparison using the equals operator. So that's what this book will talk about now. For example, the result of the following code is surprising. If we do this computation 0.3 times 3 plus 0.1, as human beings, we know that this is supposed to be 1.0, but the machine will tell us 0.999 and some number of the digits 9 followed by 8 here. And this is because of rounding error, because of the way we represent decimal numbers in binary representation. So that's the reason for that. Due to a rounding error, the value of x is a bit smaller than 1, while the correct value would be 1. It is risky to compare floating point numbers. I'll just scroll the page and place it like this. Yeah. So it says it is risky to compare floating point numbers with the equals operator because it is possible that the values should be equal, but they are not because of precision errors. A better way to compare floating point numbers is to assume that two numbers are equal if the difference between them is less than epsilon, where epsilon is a small number. So since we cannot do an exact equals comparison, what we'll do is that the two numbers that we want to compare, we'll just compare that it is less than some very tiny value. This is to account for mismatch in values due to rounding errors. Now, note that while floating point numbers are inaccurate, integers up to a certain limit can be represented accurately. For example, using double, it is possible to accurately represent all integers whose absolute value is at most 2 to the power 53. So that's a nice thing to know. And this completes the previous section that we could not complete in our last book reading meeting, which was a couple of weeks ago, I think. Now we will start a new section, and we have got a pretty lightweight agenda today. We have a couple of sections to cover, and with that we'll be done with chapter 1. So today will be a deviation from our usual problem solving activity. So the next section, the title is Shortening Code. Short code is ideal in competitive programming because programs should be written as fast as possible. Because of this, competitive programmers often define shorter names for data types and other parts of code. With this, I would say, is an opinionated section. Not everybody writes code like this. Some people do not like to write short code. But regardless, we'll go through the section. So in fact, in most submissions that I see in online judges, I do some part of this advice being followed, but not everything. So I think it depends on one's individual taste, how they want to write the code. But in any case, we'll complete this section. So type names. Using the command type def, it is possible to give a shorter name to a data type. For example, the name long is long. I'm guessing this was a pun. So the name long is in fact long. So we can define a shortened name, LL. So so what I'm doing as part of our reading and solving sessions, I'm not using these shortcuts because the point of me writing the code while solving these problems is not to do it under a time constraint, but to write well-readable code. So I don't usually follow these shortcuts, but this could be useful in actual timed contests that happen online. After this, the code long A and long B and so on can be shortened like this. We can simply write LLA, LLB because of this type def here, where we have created a abbreviation for this type. The command type def can also be used with more complex types. For example, the following code gives the name vi for vector of integers. So vector of integers has been type def to vi, so we can use vi whenever we mean this. And similarly, pi for a pair that contains two integers, like this. I'll quickly go through this section. Macros. Another way to shorten code is to define macros. A macro means that certain strings in the code will be changed before the compilation. In C++, macros are defined using the hash define keyword. For example, we can define the following macros. So capital F for first, capital S for second, and so on. So I'll not read through everything. Let's see how it is used. So for example, push underscore back has a macro pb and make underscore pair has a macro mp. So this code becomes small but cryptic like this, less readable, but could be easy to type when there is a time constraint. So yeah, so this is an example of how macros are being used. A macro can also have parameters, which makes it possible to shorten loops and other structures. For example, we can define the following macro, and this is a macro with parameters, and it has three parameters, I, A, and B. And when it expands, whatever is specified in I will go and sit here. What is specified as A will be sitting here, and so on. So an example will make it more clear. So instead of writing this whole for loop after defining this macro, we could do something like this, which says rep I 1 comma n, and this macro will expand to exactly this C++ code, because this okay, so here we are using the same dim I, so that makes it a little bit less clear. But let us say we had chosen j here, so that j becomes a parameter here, and while expansion, this would get replaced with j, this would get replaced with j, and this would get replaced with j. So it would look like for int I, j equals 1, j less than equals n, j plus plus. And what does this one come from? From the second parameter, which is an input for this a, that will go and sit here, and so on. So that's how macros work. Sometimes macros cause bugs that may be difficult to detect. For example, consider the following macro that calculates the square of a number. And if we define a macro like this, and this is a bad way to define this macro, but let's say we do this inadvertently, what would happen when we try to do this square of 3 plus 3? It would expand to this. So what we expect the result to be is 36, because what we're expecting is that square of 3 plus 3 would be the same as square of 6, which is 36. 6 squared is 36, but the answer we would get is 15, because this would be, so macros work almost like copy paste. It's just getting replaced with the expansion. So this 3 plus 3 is going to be a single argument for this a, so it would get replaced with 3 plus 3, then this asterisk operator, and then 3 plus 3. So the expansion is showed here, and then because of the operator precedence, 3 times 3 will be computed first. That would be 9 plus 3 12 plus 3 15. So 15 is the result. So the right way to write this macro, which does what we want, would be square of a equals within parenthesis a star within parenthesis a. And now when this expands, this parenthesis protects the input that we have specified, because during expansion this parenthesis would appear, and this 3 plus 3 is the argument, or is the value for this a, so it will go inside this. And this time we indeed get 6 times 6 equals 36, the correct output. Okay, so that ends the section about shortening code. Now we will move on to something that is interesting and something that is quite useful as well. And we have used some of these concepts while solving problems, solving the first few problems in the introductory problem set. So let us see the theory and the concepts behind it. So here it begins. Mathematics plays an important role in competitive programming, and it is not possible to become a successful competitive programmer without having good mathematical skills. This section discusses some important mathematical concepts and formulas that are needed later in the book. Yes, so these are going to be really simple mathematical concepts, the one that is covered in this chapter, but there are more interesting concepts much later in this book, and it will take us a few months to reach there because we are doing this book reading session only once in a while, maybe once a week or once every 2 weeks. It'll take quite a bit of time to reach there, but that's where most of the interesting stuff is. And now let us see this simple stuff that this chapter introduces. Some formulas, each sum of the form 1 to the k plus 2 to the k plus 3 to the k and so on up to n to the k, where k is a positive integer, has a closed formula that is a polynomial of degree k plus 1. So that's something interesting to note. Sometimes this knowledge can be useful for computing the time complexity as well, because we know that when we have a series like this, the final result will have a degree k plus 1. So as an example, if we have a problem, and I'm slightly deviating, I'm sort of going into time complexity because the same technique can be useful for computing time complexity. When we see that we have a problem that takes 1 steps and then 2 steps and then 3 steps and so on up to n, we can immediately know that that would be O n squared, because the result of this thing, even if you don't know the formula, we can just remember this thumb rule. The result would be of degree 2, because this is of degree 1, this is n to the 1, the powers are all 1 here, so the result would be of degree 2, so O n squared. The exact formula, of course, is n times n plus 1 by 2. That is the exact formula. And similarly, we have a formula for the sum of squares, which goes like this: n times n plus 1 times 2n plus 1 divided by 6. So these two are very popular formulas, mostly introduced in secondary school, I think in most places. So both the formulas are noted here. Both can be derived. I have in fact got a so I'll just take care of the background noise there. All right. So the background noise taken care. Now coming back to the this section. Yes. So I was saying that yeah, these formulas are normally introduced in secondary school, and we can prove this using induction, and there are other ways too. So for now, we'll just move on. An arithmetic progression is a sequence of numbers where the difference between any two consecutive numbers is constant. For example, like this. It's sometimes also called the common difference. The difference between 7 and 3 is 4, and then we add 4 to 7, we get 11. We add 4 to 11, we get 15. So this is an arithmetic arithmetic progression. The difference between two consecutive terms is going to be constant. And yes, here is the constant is 4. The sum of an arithmetic progression can be calculated using this formula. So say there are some terms in between, and we don't care what they are. They could be occurring with any difference. The difference could be 4, could be 3, it doesn't matter. The result is going to be n times a plus b by 2, where a is the first number and b is the last number, and n is the amount of numbers, or the number of numbers that we have. So if you take a look at it, it is almost like we have n numbers, and we have so there's an interpretation. There's a nice interpretation of this formula, and the interpretation is that the average of all these numbers is a plus b by 2, which is the same thing as the mean of the first number and the last number. So if you multiply that average with n, we will get the total sum. And here's a worked out example. So 3 plus 7 plus 11 plus 15 Here the common difference is 4, but this formula doesn't require the common difference. So what we do to compute this, we compute the mean of the first and the last term, which is 3 plus 15 by 2, and we multiply it with 4, and we'll get the correct answer. There are many ways to prove it. That is something we're not getting into. Okay, I've got a proof worked out on the board, so let's go through this. Let me complete this section and we'll go through the proof for this. The formula is based on the fact that the sum consists of n numbers, and the value of each number is a plus b divided by 2 on average. Yeah, so it's sort of stating this without any proof. And I will not dive much deeper into this. In case there are any questions about this, please visit our IRC channel and we can discuss this in more detail. And if more discussion is required, we can do that here. For now, I'll just show this proof that I have worked out on the board and then move on. So say we have got a sequence which goes a and a plus d, where this d is the common difference, and a plus 2d and so on. And this d could be anything, any common difference, all the way up to b. So this is the last term. If we write this whole thing in reverse, it would look like this. So s is the sum that we want to compute. We want to get a formula for this s. So this s equals the same sequence in reverse. So it's the same number, the same sequence. Not much has changed. Now, if we add this to, and we'll just do some plain algebra, simple algebra tricks, we add this to equations and we get 2s equals a plus b, and why do I have a minus b here? Did I make a mistake there? Yeah, I made a mistake there. I don't know why I switched from plus to minus. I'll just fix that temporarily here. I have to fix this later and update the website. I'll do that later. But yeah, so each one of these sums would be a plus b, and you can see this is of course a plus b. Last term is also of course a plus b. And what happens for this? We have increased this number by d, and we have decreased this number by d. So in effect, we have not changed the sum. So it is still a plus b, and so on. And how many such a plus b do we have? As many number of terms we have, and I'm noting it here. Say we have n terms. So 2s equals n times a plus b, because those many a plus b's we have. So of course capital S will be, or the sum that we were looking for would be n times a plus b divided by 2. So that is the derivation or the proof for this formula here. And if you have come this far, you can easily get this now, because 1 plus 2 plus 3 plus dot 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 n, we apply the same formula or the same understanding. So what is the mean of the first and the last term? That is n plus 1 divided by 2. How many terms do we have? N. So n times n plus 1 divided by 2. So that's how we get the formula for this simple arithmetic progression. Okay, continuing. After talking about arithmetic progression, the natural thing to discuss is geometric progression. So here it is. A geometric progression is a sequence of numbers where the ratio between any two consecutive terms is constant. For example, 3, 6, 12, 24. What we have here is a common multiplier or a common factor. Those are the popular terms. So here the common multiplier is 2, because 3 times 2 gives us 6, 6 times 2 gives us 12, 12 times 2 gives us 24. And the question usually would be, what would be the sum of all these numbers? So we'll find a formula for that. The sum of a geometric progression can be calculated using the formula a plus ak square and so on up to b, and this works out to something like this. And let me see if I worked out something on the board. Yeah, so what I usually use is this one. So this is somehow this formula is more intuitive to me than this one. So anyway, I will be showing both how we get these formulas. So in the book it is written down like this: bk minus a divided by k minus 1. The only thing I have changed in this board is change the variable k to r. So because I think of it as a common ratio, so put r here. All right, so yeah, where a is the first term, b is the last term, and the ratio between consecutive terms is k. On the board it is noted as r. And here's an application of this formula. I'll skip over that. Let us just focus on the formula itself. The formula can be derived as follows. So let me show it on the board. So S equals a plus ar square and so on up to b. So this is our each term of the geometric progression. So we add them up all and we call it a geometric series. Now what would be minus s? So I'm just putting a negative sign on all of this, so we get something like this. And if I multiply both sides with r, that is the common ratio, we'll get this. Okay, so we've got an r after each of these terms. And now there will be some cancellations, and let us take a look at that. So this AR would go and cancel this minus AR. So what we'll do is we'll add up these two equations, this equation and this equation. And when we do this addition, we'll see some cancellations. Let us see the left-hand side first. The left-hand side becomes capital S times R minus 1, that we can see here. Capital S is the common factor outside, R minus 1 stays inside the parenthesis. And on the right hand side there are some cancellations. So this AR cancels this minus AR, this AR square cancels this minus AR square, and so on it goes. So even within this dot 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 area, those cancellations continue. And what is left in the end? In the end, we are left with this minus a because nothing cancelled that. And if you see, this cancellations are going it's going diagonally like this. So this cancels this cancels this, and so on. So this b would also get cancelled by the previous term here. So that would be cancelled. This would remain. This br would remain uncancelled. So we only have two terms remaining after all the cancellations, br and this minus a. So that is here, br minus a. So now it's very easy to determine the formula for capital S. Capital S is just br minus a divided by r minus 1. The only thing to be careful about is that we're doing a division here, r minus 1, which means r should not be 1. R should not be equal to 1. And what is the meaning of r equals 1? It means all these terms are same. There's no difference, in which case we can just do n times a to get our summation. So that's the only thing to be careful about. We are doing a division here, so r cannot be 1. And I said that this is the formula that I'm used to, which I usually, like whenever I see a geometric progression, this is the thing, this is the image that pops up in my mind. Let me explain this as well. So what is the value of b? The value of b is a times r raised to n minus 1. And we can look at it here. So considering there are n terms, that is what we get. So say there are two terms only. So that would be a plus a to the power, a times r. So r is raised to the power 1. We have two terms. Okay, say we have three terms. In that case, the last term has r raised to the power 2. So the power of the last term would be 1 less than the number of terms. So that is why the last term would be ar to the power n minus 1. And if we go and do the substitution there, this would become ar to the n minus 1 times r. So r to the n minus 1 times r will become r to the n. That's what we are seeing here, ar to the n, and this minus a is seen here. So this is ar to the n minus a by a straightforward substitution in this formula with the value of b. So this is another formula worth remembering, and here's a simple application for this. So if we take 1 plus 2 plus 4 and so on up to 2 to the power n minus 1, and we say apply this formula, so we should get this. And how is that? The first term is 1, so that is an invisible 1 because we are doing a product here. The common ratio r is 2, which we are seeing here. The power n we are seeing here, minus 1 is there, and the denominator is 2 minus 1, which is just 1. So an invisible denominator 1. So that's an illustration of this formula. Okay, so I'll just skip over this because I explained pretty much the same thing on the board. It's the same thing explained here as well, and yeah, the example too, the exact example I had on the board. Okay, so harmonic sum, and this is quite interesting, so let's go through this thing. A harmonic sum looks like this: 1 plus half plus 1 by 3 plus dot 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 plus 1 by n. And this is a famous series in the world of number theory, and it is known to diverge. In fact, we can prove it that it diverges, meaning if you add infinite number of terms, it would exceed any finite number, which is another way of saying infinity. So an upper bound, but we can find an upper bound. Say we have a finite number of terms, we can get a crude upper bound. We can tell that this number is definitely going to be less than something, and it's a very crude upper bound. It's not a great upper bound, a crude one, and that upper bound looks like this: log n plus 1. So say we take 10 terms here, say 1 plus half plus 1 by 3 plus dot 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 plus 1 by 10. In that case, this we can very confidently say that that sum would be less than log of 10 in base 2 plus 1. That's what I mean. And I'm just thinking, can we do a computation and just check it out? So let me just open Wolfram Alpha. I think that would be a nice illustration just to see the exact value. Okay, so this is 1 half, 1 by 3 and so on up to 1 by 10. You can see the result is 2.92 something. Let me just use the upper bound formula now and just see how good an upper bound we get. So what we are expecting is that it would be less than this number, and this is 4.3, so it is indeed less. So this number here is indeed less than this upper bound formula, and it is a very crude upper bound. You can see it's pretty far from the actual number, 4.3, and we had 2.9. So quite a bit of error there, but it's an upper bound, so it's allowed to have as much error as it wants to have. And now let us understand why this is true. And once again, this could come useful in time complexity analysis. When we have a sequence like this, we know for sure that okay, this is going to be O of log 2n, for example. Very crude, but a simple upper bound. So namely, we can modify. Okay, let me show this on board. It will be, I think, more clear on the board. So, and whatever I'm showing here is also can be extended to show that this series diverges, and I'll come to that in a moment, but we'll first finish what the book is teaching us here. So let us say we have this sequence like this. So now what we can do, we can start replacing these terms with some convenient terms which will make our computation easier in the next step, and that we know for sure will make the series even larger. So for example, if we take 1 by 3 and replace it with half, this series will become even larger because half is greater than 1 by 3. And same thing here. So 1 by 5, we are replacing it with 1 by 4. So this is like 0.2, this is 0.25. So we're always replacing these terms with something that is larger than what we have here. So that's the technique we are using. And how do we know what to replace? So we're going in powers of 2. So 1 remains as 1, half is copied as half, 1 by 3 is replaced with 1 divided by a power of 2. So the power of 2 that we are seeing on the left side. So we replaced it with 2. Now again, we have hit a new power of 2 in the denominator. We copy it 1 by 4, and all this 5, 6, 7, which are not powers of 2, we are just replacing it with this power of 2 that we have encountered so far, 4. So 1 by 4, 1 by 4, 1 by 4, 1 by 4. And all of these terms are bigger than the terms here. That is why we put this less than equal to sign. And we continue the same technique. 1 by 8 is of course 1 by 8 because it's a power of 2 in the denominator. This is not a power of 2, so we replace it with 8, 10 with 8, and so on. And we can keep doing this thing. So what we have done so far is we have guaranteed that this sequence here is going to be less than equal to this sequence. And now it is easier to work with the sequence. We can get a nice formula. The one little change that we'll do now is, okay, so let me first explain why we will do a change here. So this has a sum of 1. This is just a single number 1. This has a sum of 1. This also has a sum of 1 because this is 4 times 1 by 4, which equals 1. This is not 1 yet. This is 3 by 8. So what we will do as a hack, we'll just add more number of terms so that this also becomes 1. And the good thing is it does not change this inequality. We can still continue with less than equal to, because what we have done is added more terms. So from here, we have come here. And now each of these terms is 1. And how many such groups we have? So we have one group here, second group, third group, and fourth group. How many such groups do we have? Turns out we have log 10 to the base 2 plus 1 number of groups. And how do I explain this? Let me just cut off the sequence, say here. Okay, so if we were cutting off the sequence here, we have 7 terms, and we have 3 groups. And how do we go from 7 to 3? And we know that we are increasing it in powers of 2. So log 7 to the base 2 would be 2 point something. And when we add 2 point something and this 1, that becomes 3 point something. And we know, and that sort of captures the fact that we have found an upper bound which is greater than or equal to 3. So when I did this cutoff, when I cut off the sequence here, for this specific case, we want to count how many groups? 1, 2, 3, and 4 groups. So we are representing this log. So what this log 10 2 is representing, it is representing 3 point something, because 2 to the power 3 is 8, 2 to the power 4 is 16. So 2 to the power 3 point something would be 10. And in fact, let me just show the exact number in case that helps with the imagination. So 2 to the 3.32 is 10. So like I said, it will be 3 point something, and 3 point something is representing these groups that we have encountered so far, and this +1 to make sure there's no error. Okay, so I don't think I did a very good job explaining the inequality there, but I'm pretty sure if you just work it out on paper and compare the number of groups with the way this log is increasing, it should match up. So I'll not try to spend more time there. I did not make a very rigorous board here on purpose because it will take more time to explain that. But regardless, this is a good thumb rule to have. And anytime we have a sequence like this, we can invoke this as an upper bound. Could be quite useful for time complexity analysis. And here's the general formula noted here once more: 1 plus half plus 1 by 3 and so on is less than or equal to 1 by log 2n. And like I said, this also sets the intuition for the fact that this sum actually diverges. So if we add infinite number of terms on the right hand side, we can just keep doing this grouping and get infinite number of ones here. No, that is not a good proof for the divergence, because that is only establishing an upper bound. I think what we need to do in that case is need to do the grouping differently, where we set a lower bound. Like we say that each one of these groups exceed that one we have, but I have not prepared a board for that, so I'll just continue for now and not go into the divergence of this series for now. Maybe some other time, maybe this book also has it, I don't know. So for now, we'll just understand, just stop with this inequality. Couple of more pages remaining. Let us just see what is there. Set theory and logic. Okay, quite a bit of stuff remaining. So let's see how far we can go until the next 10 or no, next 7 minutes that we have. So set theory. A set is a collection of elements. For example, this set capital X equals 2, 4, 7, and this is a set of elements. The symbol phi, I think, is this phi. Anyway, I'll just call it the empty set symbol. So this symbol denotes an empty set, and this notation, which is capital S with bar on both the sides, denotes the size of a set, the number of elements in this set. So the number of elements in capital X is 3, so that is noted here with this notation. If a set S contains an element X, we write this notation: X belongs to S. If it does not, then we write this notation: X does not belong to X. For example, in the above set, 4 belongs to X and 5 does not belong to X. This notation. And these things I'll just quickly skip over, because these things are, I'm pretty sure everybody would be familiar with this notation. This is A intersection B, the common elements in both sets. A union B, we're just combining, making a union of all the elements in both sets. For example, here's an we have A equals 3, 7, B equals 2, 3, 8. So A union B will be the union of all the elements. So we are counting all the elements. So 2, 3, 7, and 8. All right. Next, we continue the complement. And in complement, we have this concept of a universal set. I would just request a confirmation that you can still see my screen fine. I have a second display open and it is not showing my own screen to me. So just, if somebody can post a message on chat and confirm that you can see my screen fine, then I would know that my client is working fine. All right, so it's visible. It looks like the display, the tab on the display has a problem connecting to Jitsi. Maybe that's the problem there. All right, so continuing. So whenever we talk about complement, there's the concept of universal set that depends on the context. Sometimes the universal set could be, say, a set of all integers. Sometimes it could be something else. So that is explained here. The interpretation of a complement depends on the universal set, which contains all possible elements. For example, if A equals 1, 2, 5, 7, and the universal set is all the numbers from 1 to 10, then the complement would be computed by taking this set and removing all the elements from here. So that's how this works. And then we have the concept of difference where so this is the formula, A intersection B complements. In simple words, we have all the elements in A, we just remove those elements from A which are present in B. For example, 2, 3, 7, 8, we remove 3, 5, 8 from here. So 5 does not exist, so we don't have to worry about that. We remove 3 and 8 and we get 2, 7. In each element of A also, if each element of A also belongs to S, we say that A is a subset of S, denoted with this symbol. A set S has always 2 to the power the number of elements in S. So this is the number of elements in S subset. So as an example, okay, there's an example here. If a set has 3 elements, then we can make 8 possible subsets about it, and it is just a simple binary calculation. In each subset, we can decide whether to pick an element or not to pick an element. So 2 possible choices for this. We can pick it, not pick it. 2 for this, 2 for this. So that's how we get 2 times 2 times 2 equals 2 cubed. So that is the justification for this formula. Some often used sets are natural numbers, Z for integers, and there's an interesting story about this. Why is Z used for the set of integers? In German, I think integers are called Zahlen. There's a word called Zahlen in German, and that is where this symbol Z comes from. There's a nice note about it on Wikipedia about this. The set n can be defined in 2 ways depending on the situation, either n equals 0, 1, 2 or n equals 1, 2, 3, and so on. And then we can also construct a set using a rule of the form, and we can see this here. For example, we can say, okay, this is a nice example. We'll just look at this directly. So this is called the set builder notation. So here we are saying that we're forming a set capital X where each element is 2n, where n belongs to Z. So this becomes a set of all even integers. For each n, we are taking 2n as an element. So if n is 0, then we get an element 0. If n is 1, we get an element 1. If n is 2, we get an element 4. If n is minus 1, we get an element minus 2, and so on. So that's called the set builder notation. It's very much like list comprehensions in Python. So if you see a list comprehension, we use a similar syntax, so a sort of like set builder syntax to express something like this. So let me just open a new board. I think something like this would be like this in Python, 2 times n for n in, okay, we cannot have an infinite set in Python, but maybe something like this, and I can only have a finite set to choose from. You can see it's very similar to what we see in Python. So I think the Python list comprehension syntax is inspired by the set builder notation. All right, so this is where we will stop. I had hoped to complete this chapter 1, but it looks like it's a big chapter. We'll continue with this remaining chapter in the next book reading session, which will be a few weeks from now. Before I end this session today, let me just show the website again, because we'll not be meeting for some time. So I'll just show where the schedule is kept. So if we go to offpay.cc, which is the main page for this website, from there we can drill down to this specific book club meeting that we're having, which is the CSES problem solving. So this is where we go, and past and future meetings is here. So meeting log, past and future meetings. we currently had this meeting, the meeting number 8, which we just completed. And you can see the remaining schedule here. We'll meet again on 16 November, which will be roughly 2 weeks from now. That's when we'll meet again, and we'll continue with the CSES problem set. The next problem coming up is Tower of Hanoi, creating strings, and then more problems after that. Yeah, so this is where we stop. There's one more thing I will show. If you go to offpay.cc, here is the link to our chat room or the IRC channel. This is where all the community members hang out, and this is where we also discuss schedule updates. And if anyone needs any help, or they just want to discuss their own solution or share solutions, this is where we do it. So once you land on the offpay.cc homepage, you can click on either of these links and visit our channel. If you're not used to IRC networks, I would recommend this link, the second one, because this way you can connect to the channel once and stay connected even when you close your browser and go away. That would be difficult to do with this thing unless you are used to IRC and you know how to set up IRC bouncers and so on. So if you're not used to IRC, I would recommend click on this link so that your session stays alive even when you disconnect. So when you connect back, or when you open your system again the next day and open your browser and come back to this channel, you can see all the conversations that you have missed since the previous day. So that's why I recommend the second link. All right then, so that is all for today. We will not be meeting for a couple of weeks, and then we'll again continue with the remaining problems, the first one being Tower of Hanoi. So until then, take care and goodbye. See you after a few weeks.